Hello, fellow hams! In association with the Frederick Amateur Radio Club, featuring the three amigos of the Palomino Antenna Workshop, my name is Sandy, KB3 Echo Oscar Foxtrot, and this video is to show how to model and properly construct a dual-band copper pipe J-pole antenna. We'll start off by doing a Google search of MMANA-GAL Basic. And the first item that pops up is an antenna analyzing and modeling tool that we'll be using for this presentation. Go ahead and click on it, and then scroll down or page down one and look for the Download MMANA or MMANA-GAL Basic version. This is a free Windows program that also happens to run under Ubuntu Linux using Wine, which is what I'll be using for this presentation. Go ahead and install it and bring up the main screen. First, let's open the stock antenna section. And you'll notice that they have lots and lots of antennas. Any antenna you can imagine. Under VHF, we have JAntenna144.MAA. That's the J-pole, the library version. And you can see the classic J-pole shape. As we zoom in a little bit, let's orient it so that we're getting a broadside view. And we'll select each individual wire so we can see how all the wires are labeled. This would be wire number 1 highlighted, wire 2, which is on the right hand side, wire 3 is just below this crossbar in the middle, which is the feed point, wire 4 is the bottom, wire 5 completes the loop on the bottom, wire 6 is the left-hand side, or the short pole of the J-pole. And wire 7 is the feed point. This would be where you would attach your RG58 or whatever you're using to feed your J-pole antenna. Let's start the simulation by hitting the Calculate button. And we see that the frequency is 145 megahertz, the 2-meter band. It's 7 meters above real ground and made of aluminum pipe. We'll go ahead and start. And we see that we get an SWR of 1.03, which is pretty good. It's well tuned right out of the box. Let's look at the currents. You can see that this has the opposing currents on the lower part of the J-pole. These cancel out, so there's no radiation from the lower part. The upper part is unopposed, and so you get a nice radiation pattern coming from here. If you look out on the far field plot, it goes out to the sides. There's a big null up on top. This is exactly what you want. Let's take a look at the SWR plot and get an idea of what the bandwidth is under an SWR of 1.5. And you can see you only get a megahertz or so on each side. So not the best bandwidth in the world, and we can probably do better than that. Let's see what happens when we move it up to 448, because it should resonate at on the 70 centimeter band. Let's see what happens. 448. We start. Not so good. 2.64 SWR. Let's take a look at the currents. And you see that the unopposed part is still not broadcasting. We get 3 lobes up top. And if you look carefully, though, you can see that these lobes will be out of phase with each other. So while the electrons are going up here, they're going down here and up here. And conversely, when they come back, they're going down here, up here, and down here. So this current opposes this current and this current, and we get a far field plot with a big null right on the side in addition to the top one. And most of the signals heading out to the stratosphere, not to your buddy or to the repeater. So we can do better than that. Let's see what improvements we can make on this design. To improve this antenna, let's add a trap to the middle of the upper segment. And let's also change over to, let's make it copper pipe. We'll keep it at 7 meters above the ground and keep the ground real. And let's see how that affects this SWR at 446 megahertz. All right, a little bit of improvement. We got an SWR of 2.02. Let's look at the currents. Yeah, we're kind of opposing the current here, letting this and this be the dominant currents. Let's see how that looks on the far field plot. Okay, well, we've improved that null on the sides, so we're getting some signal out on the side now. And let's see how we're doing with SWR. And we're still, we're kind of way off the other end here. Let's see where this is resonating. Look, I'm guessing it's going to be about 440. Let's try that. Yeah, we got a better SWR there, 1.39. All right, so we have 4 megahertz below 1.5, but we're almost off. Well, we're way down at the left-hand side of the band for 440 meters, and the SWR is not that optimal. We should be able to do a little bit better than that. Let's also check out how we're doing at the 2 meter end. So we'll go to 145, start that up, and we kind of ruined it. 3.3 SWR. Let's see what the currents are doing. Yeah, there's a significant amount of current occurring on this trap, even while it's going through the 2 meter band. So we want to minimize that at this frequency. Far field plot, about the same, doesn't really affect that, but check out the SWR plot. And again, we're way off the end of the 2 meter band. So, yep, we got some optimizing to do here. To optimize this new antenna for the 146, 446 bands, we have a couple of toys we can use to play around here. Let's go to Geometry and put the Keep Connect button checked. That makes sure that every element that is connected to its neighbor stays connected, even if we only vary one of them. And let's check out the tools we've got. Optimization. We can set the band 146 and 446. So we've got the dual band capability. This will optimize both of them at the same time, which is nice. Let's set the environment. Azimuth 0, that's broadside to the antenna. And the vertical is the elevation of 5 degrees. We want to have a nice low elevation coming out the sides. That's okay. The main thing we want to optimize is the SWR, the impedance, and the elevation. The rest of it can float where it may as far as the optimization is concerned. Now this specifies which wires we want to vary. And this is the position of the wire, and this is the points. We're only going to vary the Z points, so up and down. And if we've got a 0 by it, that means it varies independently. If we've got a 1 by it, that means it's varying in conjunction with another wire. So wire 9 is horizontal. If we vary 1, which it's attached to, we want to make sure it stays horizontal. Same thing with wire 7. We want to make sure wire 7 stays horizontal. So if you move the Z1, we want the Z2 to do exactly the same thing. So let's go ahead and start that up and see what happens. You can see that things are moving around. Segments are jiggling. It's going back and forth between the two frequencies, and we came up with a result. Let's see if that improved things. All right, well, we can see for 446, we've got a SWR of 2.07, which is not bad. We still have a bit of a indentation on the side, so we've got some room to work with. I think we can do better than this. Let's see what the plot is for the SWR. And we're still off the side of the band. Well, okay. If the antenna is a little bit too small, it's resonating at the high end of the frequency, we can actually scale that with this tool. And we could make the antenna a little bit bigger, and then go ahead and increase the size of that overall. All right. Well, let's see what happens at the 146 segment. And let's start that up. Okay, we're getting there. 1.66 SWR. Far field plot hasn't changed. We can look at the SWR. Yeah, now we're too big. All right, so clearly we need to do some iterations of this and keep changing the values until we reach a happy medium. So let's go on to the next result after we've done all that. The final result is an antenna I think we can all love. Let's see how it does on the 446 frequency. 1.03, not bad. Let's look at the currents, and you can see we've shortened the trap somewhat. It gets lots of current on this particular band, and we have prominent lobes top and the bottom and the top of this upper part of the pole. So look at this. Far field plot shows the signal's going way out to the side. Very nice. Like that. Let's see how the SWR plot looks. Oh, we don't want to do that. We want to do detailed. And look at that. We got below 1.5 almost through the entire 440 band with a whopping 8 megahertz of SWR below 1.5 and a nice low SWR right in the middle of the band. This we can work with. All right, well, how about the 146 frequency? We do spend most of our time on 2 meters, so did we manage to get a winner there? 1.0 SWR. I'm liking this design. Let's take a look at the currents, and we see that, yeah, very little current on the trap. The trap is working exactly as designed. The 146 frequency does not hardly register at all here. Goes right on through it. Broadcasts like a champ off this top section. Let's look at the far field plot. We still got our nice far field plot putting the signal out to the side. And how about our SWR plot? Let's take a look at that. And look at that. We got a 4.3 bandwidth under 1.5 SWR. That's the whole band. So we've got the entire 2 meter band as well as the entire 440 band with a nice low SWR in both. That, my friends, is the antenna we want to build. Okay, ham radio enthusiasts, you have seen the results of the MMANA software emulator and how great an antenna we can possibly make. This is the final result. We have separated out the parts because even though we know the measurements of how much it should be from the center of the pipe to the center of the pipe, and from the center of the connectors to the center of the connectors, once you put these inside, you'll notice that they don't go straight from the center. They kind of end here. So we had to do some finagling, and to make it simple for everybody, we have put the measurements of what the actual pipes ended up being. So for your ease, you can just cut to length. This one is the main pipe, and it was 1.031 meters. All right. Then we got the T and the elbow, and this little connector, which is 3.7 centimeters. This is the trap for the 440 band, and this turned out to be 13 centimeters long, exactly. And this is the top of the antenna, which was 38.1 centimeters. Now we go around to the bottom of the J. Thank you, Mr. Cameraman. And let's start with this. This was our crossbar, and we wanted to make it approximate a round pipe because that's what we modeled, and that's what the model demanded. If I just substituted a thin wire, it didn't work, or I could never get the great results we got. So this approximates the roundness of a solid bar between it, and you can see we've got the outside braid onto, it would go like this. The outside braid goes to the short side, and the center conductor would go on the long side. All right, so it actually goes like that. And then we get the T connector at the bottom. It's got the hole in the bottom here so you can put a pole in and support the whole thing. Then we got another short connector that is 3.7 centimeters long, exactly, same as the other one. And another elbow to the left-hand side of this J, which was 50.3 centimeters long. All right, now to give a little bit more detail on the pigtail here. This is RG58 coax with just a, what was it again? A PL
SO239.
SO239 connector. So this is what we used.
What's that made of?
Oh, good point there, Steve. This is a copper hanger strap that you can get from Home Depot. Comes in 10-foot sections.
Copper plated.
It's copper plated steel is what it is. And you just wrap it around there and then put a bolt through it so you can tighten it. And then I cut one side short and the other side long and did the opposite on the other side. And then we solder, because it's copper, it solders pretty easily onto the surface of this strap. This steel is pretty stiff and doesn't easily bend around this copper pipe. So you have to kind of use a little technique here. I like to have 3 holes for the bendy part and put the bolt through these 2 little holes when we get it all bent, because then it doesn't slip, the head of the bolt doesn't slip through the hole, the bigger hole. Use a little hole. So when you try to bend this around, you're going to notice that, all right, it's not working very well. What do I do? Okay, here's the trick. Make sure your little holes are lined up, and then use your friendly neighborhood vise. But this will kind of get it on its way. And of course, make sure you have permission from the local vise owner before you bang on his vise.
Oh, that's optional.
All right, then again, making sure that it's even. And you got the 3 holes on top. Let's see if we can't get it tighter this time. So I like to kind of press it down and then give it another squeeze. Ah! See, look, now we're getting better.
Nicely done.
All right, then release. And see if you can fit, well, take it off of the pipe. And then see if you can put a bolt through there. All right. I failed to mention before, the size of the nuts and bolts that we use is this. There we go. Number 8, 32-32 by 1/2 inch. This is the Palomino separator, because no antenna is complete without a 3D printed part. And we put this on here in order to make sure we have the proper distance between the 2 arms of the J-pole at the very bottom. So that goes on. There we go. And we put that on there. Now, in order to attach this pigtail, we're going to put it between these 2 leaves here. We're going to need to insulate the base of it with a little bit of electrical tape, because one side is going to go this way and the other side is going to go that way. And we want the base side to go to this one, so it'll go like this. And we don't want this part here to come into contact with the copper. So we're going to have to put a little bit of electrical tape around there to insulate it before we do any soldering. So this kind of goes like that. Wrap that baby around. All right, we have taped and now tinned the 2 ends, the braid and the center conductor, placed it between these 2 leaves that we have secured in place with the nuts, and now we're going to solder them to these surfaces. This is a quick slideshow to demonstrate the results of our soldering efforts. This was the center connector. Here's the braid being held in place with a hemostat. And we soldered it. Notice we did not melt the center coax, thanks in part to the electrical tape wrapped around that. Now that we've put the antenna together, soldered all the parts, and made sure that it's correctly attached to the pigtail to feed, it's time to take it outside and slowly move this strap up and see if we can't tune it to the SWR that we were promised.
I just got an urgent call from Sandy and Kurt that they have an incredible measurement. What do you got there, Sandy? Let's see.
It's right there.
Let me
Can
get
you see it?
the
It's hard to see.
okay. And that shows 1.02 SWR at 146.2 Not bad. 1.02. What are you going to do to try to get it any lower?
Well, show what we've got up there.
So we're out here in 60-mile-an-hour winds, and he can barely keep the antenna in the air. There you see it, 1.02, baby.
Let's do 440. All right, 440 is wavy, but it's 1.12.
Got a question. Am I supposed to hit record?
1.02. So yeah, 440 is a wavy thing, which we expected. Okay, we're good. After our initial success at putting the antenna together and measuring the initial 2-meter band SWR, it's time to set this up out in the field and see if we can get actual successful communications from point-to-point simplex. Here I've set up our S-shaped J-pole on top of a long kite pole. It's about 20 feet, maybe 25 feet up in the air. And this is in my front yard, and I'm going to attempt to communicate with Kurt. We see we've got a curve that stretches from 450 all the way over to 420. Right here is the 1.5 SWR line. For the entire frequency of the 440 band is below 1.5 SWR, and it reaches a low point of 1.01 at 439. The wavy nature of this curve is because of the RG58 feed line. You get a little bit of reactance as you go up and down that line. But it all is where we want it, and this should radiate very well. When we started up communicating on the 2-meter band, we see 1.05 SWR. All communications were loud and clear. Couldn't have been better. We were very happy with this simplex conversation. When we moved up to the 440 meter band, 1.01 SWR, and very happy with the result. Finally, let me point out that not every antenna turns out perfectly. Due to circumstances beyond our control, sometimes you may end up with an antenna that resonates off to the side of the band and has an SWR that heads off to the stratosphere on the other end. And you have to figure out a way to salvage this situation. Fortunately, there are things we can do about this. Go ahead and buy a couple of end caps and sleeves. These are 1/2 inch. Get the sleeves that don't have the little indentation so you can slip it all the way down on the end of the pole. Put the end cap on the short pole and the sleeve on the long pole, and then adjust your crossbar to the feed point up a little bit and see if you can't get a better SWR. You can continue to adjust these up and adjust the crossbar, and hopefully eventually you'll get something like this. Perfect SWR, a lot better in the center, and a lot more happiness. Good luck, my friends. Well, ham radio operators, I hope you have many happy contacts with this antenna. Here is a summary of the measurements if you wish to construct one of these yourself. To tune it, start the strap about 3 centimeters from the bottom edge to the top of the bottom pipe and advance it up 1 millimeter at a time. Measure the SWR at 146 megahertz until it reaches a minimum. It should tune easily. We have built several of these antennas so far, and they've all tuned up within just a few minutes. I hope you have the same results we do. We also hope to hear from you on the air with your own Palomino J-pole. 73, my friends, this is KB3EOF, and I'll be clear.